if I'm taking any variable like pressure, volume, right, or even it can be temperature, if I'm taking them as my functions or as my variables, if that function has to be a state function, either temperature or volume or pressure, whatever it is, if any one of them, if any one of the variables or any one of the functions, if they have to be state functions, they have to follow certain rules. Those rules are, the first one, suppose if you believe, if I'm generalizing a variable phi, okay, this phi can be any value. It can be pressure, it can be temperature, it can be volume, it can be entropy, it can be enthalpy, it can be any function. If this phi is considered a state function, if it is a state function, then it has to follow a rule that, see, suppose if the initial state, suppose if a system is studied from one state to another state, state A to state B. Suppose if I am studying a cup of hot water, let it be. I am studying from this state to this state. Just I want to measure how much the volume of the system is changed from A to B. Here my system is hot water. So how much the volume is going to be changed, I want to study. If I believe that volume is my function, if that volume has to work as a state function, then it has to follow the following rules. That is, firstly, if it has to state function, it depends only upon initial state and final state, right? That's what I said yesterday. It never depends upon the path through which the final state is reached, correct?
Yes, sir.
Therefore, I can tell that the change in volume in this process from state A to state B, it purely depends upon its initial state and final state. Therefore, at initial state, I am considering it is phi A. At final state, I am considering it is phi B. Now, the difference between them, that will give me simply the change, right? Suppose if it is carrying out in a reversible process, or if you are checking very small change, that is considered d phi, correct? And you are taking the process throughout from A to B. Therefore, from A to B, you can take up integral A to B. Understand? I repeat once again why this equation is taken. I am taking any function, suppose phi. Phi is my function. If that function has to be a state function, that has to follow this rule. So this rule means, suppose if I am counting the phi, if I want to check the phi value of this hot water, when this hot water is transformed from state A to state B, if phi has to be state function, the change in phi must depend only upon state A and state B. It never depends upon the path through which it is carried out, either this path or some other path, no matter. It depends only upon the initial state and final state. Therefore, the change in phi is given by difference between phi A and phi B, which is nothing but d phi. And this d phi you can calculate between any 2 points. Suppose instead of counting A to B directly, you can take up from A to some other point this, and some other point this, some other point this, some other point this. Suppose for this small change, if you want to calculate, you can calculate, right? And next, and by that way, by bifurcating or by splitting the entire path through which the final state is reached, you can again sum up all, or you can integrate them all to get the overall change. Therefore, here integral from A to B stands for from state A to state B, the overall change in that state function is given by phi A and phi B difference. Therefore, this is a mandatory condition required this is the first mandatory condition that any state function has to follow. Integral a to b d phi is equal to phi a minus phi b, or strictly speaking, always the difference is taken from final state to initial state. Therefore, since I have taken b is the final state and a is the initial state, it would be better meaningful if I write integral a to b d phi is equal to phi b minus phi a. It would be better. Final minus initial always. It makes some sense. Okay. Of course, nothing wrong even with phi a minus phi b, but we will get some negative value. Negative of this is also nothing but phi b minus phi a. Second. Okay. Therefore, you can tell that this phi value depends only upon the initial states A and final state B. It is independent of the path. Next, second condition required. Suppose if you believe phi or phi is a state function, and if you operate the process in a cyclic process, this point already we discussed. Suppose this is point A and you're doing somehow, and again you reach the final point B. Here A nothing but B. If it is the case, definitely the change in state function phi b minus phi a nothing but 0, which is equal to, it is d phi, and you are taking integral. It's a cyclic integral. Therefore, either you can take up from point A to A, or even you need not to write, right? Because again, it is started from A, again it is reached A. Therefore, there is no point of writing A to A, even though it means same. So this symbol itself indicates the cyclic integral. This symbol itself indicates you are started from A and again you reached A. Understand?
Yes, sir.
Therefore, you can directly write cyclic integral d phi is equal to 0. Therefore, this is one condition required and this is second condition required in order to be a state function. There is another important condition, that is third one. Suppose if phi is a function of x and y. Here x and y stands for if they can be pressure, volume, temperature, or any two variables. So x and y are any two variables. Suppose if phi is a function of x and y, then in that case, it has to follow an important rule that is called Euler's reciprocal rule. So about Euler's principle, you will study in higher mathematics, maybe in BTech, not even in intermediate stage. But this principle is required. Let's see what do you mean by Euler's reciprocal principle. So as we have taken this function, suppose if phi is a function of x and y, then first what you have to do, you can differentiate this function with respect to x by taking y is the constant. So I'll write here dou phi by dou x. So what I did, I differentiated this function with respect to x by keeping the other variable constant, the other function constant, that is y is constant.
Like partial differentiation.
Yes, partial differentiation I'm doing. And next what I have to do. So initially the first step I did is I differentiated phi with x. I got one term. Next what I have to do, I have to differentiate again with respect to y. This entire term, I need to differentiate with respect to y by keeping now x constant. Understand?
Yes, sir.
Okay, this is one. Next, another term. So previously what I did when I took phi is a function of x and y, first I differentiated with respect to x. Now what I do, first I differentiate with respect to y, that is dou phi by dou y by keeping x constant. Okay. Next, I have to differentiate the entire term by the next variable, that is with respect to x. This entire term has to be differentiated with respect to x by keeping this entire term at which y is constant. Now these two values must be equal with each other. When these two getting equal, then this phi is said to follow Euler's reciprocal principle or Euler's reciprocal rule. Understand? So basically the meaning of this Euler's reciprocal principle, you will all the details you will get to know in higher mathematics. Okay. Okay, they are the three important mandatory conditions for any function to be a state function, to become a state function. Okay, so I'll give the notes right now. Any function if has to be a state function, the following mathematical conditions must be followed. The following mathematical conditions must be followed. Right, the first one. If phi is a state function, so write down this one. Phi b minus phi a, which must be equal to d phi integral from a to b. Integral a to b d phi is equal to phi b minus phi a. It means, write down, it means change in phi depends only on initial and final states. But not on the path.
Excuse me, sir. Can you repeat this statement once again?
The change in phi depends only on initial and final states, but not on the path. Next, second point. Integral d phi equal to 0, or cyclic integral d phi is equal to 0. This is second condition. Cyclic integral d phi is equal to 0. Third condition. So write on this line, if phi is equal to f of x comma y is a state function, Euler's reciprocal theorem must be satisfied. Euler's reciprocal rule must be satisfied. So write down that Euler's reciprocal rule.
Sir, can you spell that Euler's spelling?
EULER. Euler's.
Thank you, sir.
Next, write one question. Prove that pressure of a fixed amount of an ideal gas. Prove that pressure of a fixed amount of an ideal gas is a state function. Is a state function. Is a state function when P is equal to nRT by V. When P is equal to nRT by V. Okay. So for that, the first two conditions, anyhow, every state function automatically follows. There is nothing special in that. Only the thing is you need to check the third condition, that is Euler's reciprocal rule directly. Just do that. So here in the above equation, whatever the phi you take, you have taken out here, the phi nothing but pi, P, pressure. Okay, and in this equation you can see P is proportional to n r times of T by V, correct? Because they are constants. Therefore, only the variables are temperature and volume. Therefore, you can write here P is a function of temperature and volume, correct? From this equation, yes or no? P varies
Yes,
based
sir.
on the temperature and volume. P is independent of constants, correct?
Yes,
Therefore,
sir.
Yes, sir.
now can you try this by taking this equation? P is a function of temperature and volume. Therefore, can you check that first calculate it, and after that calculate it, keep it aside. Similarly, do that first, calculate about it, next calculate it. Now check this value is going to be equal to this value or not.
Sir, are we supposed to multiply y over there? Like we have dou phi by dou
This
x.
one, no, it's not multiplication. You're differentiating this entire term again with respect to
Sir,
dy.
got it.
No, sir. Like I meant like you wrote dou phi by dou x bracket and then you wrote y, right?
This one,
Yes, sir.
that is at constant y. This is constant.
In order to tell that y is a constant.
Yeah, suffixes. These suffixes are speaking about constants. So first, what you have to do? What would you do? First, dou P by dou T at constant
sir.
volume. You
Yes,
have
sir.
to do that. Dou P by dou T at constant volume. So just differentiate this one with
NRV, sir. NR upon V, sir.
NR upon V. Correct.
Upon V.
Yes. Next, what you have to do? You have to differentiate this entire.
Differentiate with Y.
Yes.
V, sir.
Dou P by dou T under constant volume. This entire term has to be differentiated with respect to
V, sir.
V under
V.
constant temperature.
Temperature.
That means differentiate this entire term with respect to V. What will you
Yes,
get?
sir. So minus
minus,
NR upon V square.
correct. So
So
this
same
is
with the reverse process I did it, sir.
okay, good. Similarly, calculate this one. Definitely you would get minus NR by V square. All YPC students, you guys need not to worry about it. Even for MPC students, the proofs are not required. Just to get an idea, I'm giving this information.
Could you show the other formula, the one with circle, cyclic process one?
Cyclic integral.
Yes, sir, the cyclic integral.
Cyclic integral d phi is equal to 0.
That's it.
Cyclic integral d phi must be equal to 0 if phi has to be state function.
Got it.
So got everyone? That one, other one also?
Yes, sir.
Next. Now next let's move to very important area, that is called work. So what do you mean by basically work? What do you mean by work?
A change in energy.
Yes. Work nothing but it is the energy transformation, right? Can you tell it is nothing but energy transformation from one system to another system? Basically, suppose if there is no temperature difference between the two bodies, if energy is transformed from one body to another body, even though there is no temperature difference, can you call it as work?
Yes, sir.
Suppose if there is temperature difference, heat energy transformation happens, but that energy transformation we call it as heat, right?
Yes, sir.
Yes, sir.
If there is temperature difference, even you can carry out energy transformation between two systems or between two objects, even though they do not have any temperature difference, correct?
Yes,
Yes,
sir.
sir.
So that situation is called work. Therefore, work nothing but, of course, you would have learned a basic level definition. Work nothing but force into displacement, right?
Yes, sir.
For
We
any
have done
for
it.
any
Yes,
mechanical
sir.
work,
So even
force into
energy one we learned.
Hmm.
Even energy definition we learned, sir, for work.
Right. Okay. Therefore, you can simply say energy nothing but the it is the work nothing but it is the energy that can be transmitted from one system to another in such a way that the difference of temperature is not directly involved. Correct?
Yes, sir.
Okay. And the way of understanding, DW work done. That means you're focusing on very small work done or work change. DW can be taken as directly some force into displacement, correct? Some dx. Dx is the displacement. Let it be.
Yes, sir.
Okay. And how would you get this force? How would you get this force? The source from which this force is getting in that process. Depending upon that source, this work can be defined. It purely depends. See, you're getting that force that matters. That force can be arised even by electrical supply, correct? Electricity
Yes,
supply.
sir.
Yes, sir.
And it can be done even by gravitational force,
Yes,
gravitational
sir.
supply.
Yes.
And it can be done even by magnetic field.
Yes,
Yes.
sir.
And maybe there are some other sources as well. Therefore, the displacement of any object happens because of this force, and this force can be supplied by any virtue or by any means. So depending upon the source, how this force is being is supplied, the work is defined, whether it is mechanical work done or electrical work done or expansion work or non-expansion work, right? So that depends upon the source from which that force is being supplied.
Yes, sir.
And let's see, Anyhow, time has come. I'll give you one important unit which will help you while solving numerical problems. PV nothing but work done, right?
Yes, sir.
Yes, sir.
Energy work done. Yeah, we can say.
PV nothing but work done. And you know what is the unit for pressure? If you take up 1 atmosphere for the pressure and for volume liter, therefore you can take up 1 liter atmosphere is the common unit for PV.
Yes, sir.
It is indirectly speaking about work. 1 liter atmosphere nothing but work. But most of the times work is expressed in terms of joules, correct? Or sometimes
Yes,
even
sir. Joule.
in terms of calories. So it would be better if you know the relation between liter atmosphere and joule. 1 liter atmosphere, nothing but it is almost 101.3 joules or around 24.2 calories. So important. So quite important it is relation between or the relation between liter atmosphere and joules. Okay. Now let's see the work done in terms of pressure volume. PV work analysis. Let's see it. For that, suppose if I'm taking a closed cylinder, let it be a closed cylinder. This cylinder is, suppose if it is fitted with uh, a freely movable piston, let it be a freely movable piston. Let's say the overall length of this vessel is, let it be L, and let's say this is the length of the vessel in which some gas is taken. Suppose this is the length of the volume, let it be some x, in which gas is not available, right? Yes or no?
Yes, sir.
In this area. Therefore, you can tell the length of the vessel which is in which the gas is available is indirectly L minus x,
Yes, sir.
correct?
Yes, sir.
So we need this length. Length of my system, nothing but L minus x. And the area of that vessel, if I'm considering some A, simply by multiplying this A with L minus x, I'll get the volume of my system, correct?
Yes, sir.
Yes, sir.
Therefore, I can take it up volume of the system is some A times of L minus x.
Yes, sir.
Okay. And suppose if I want to compress this gas, if I apply some external force from outside, what will happen? Piston will move in the downward direction automatically.
Yes, sir.
Yes, sir.
Here, work is done on the system, yes or no? Here, work
Yes,
is done on the gas because gas is being compressed. So, how much work is done? That I want to check here. Understand?
Yes.
For that, first I'll take up the general expression. dW is nothing but force multiplied by the displacement dx.
Yes, sir.
And you know, because of see the pressure you can measure even in terms of the force you can measure even in terms of pressure, right? Because pressure nothing but force per
Force per area.
unit area.
Force per unit area.
Therefore, force nothing but you can write pressure into area, right? Therefore, I'll rewrite force nothing but pressure into area into displacement, correct?
Yes, sir.
Yes, sir.
Therefore, here I can write uh, continuously I'm getting calls.
you are on mute, sir.
Okay. Therefore, here work done nothing but pressure into area of my system, or maybe the vessel in which the system is taken, into dx stands for the displacement indirectly. How
Yes,
much
sir.
displacement it is? Maybe suppose initially if it is there at this location, if it is compressed up to this location, this is my displacement, correct?
Yes, sir.
That's what this dx is speaking about that. Therefore, uh, overall product of all the three will give me the work done.
Yes,
Therefore,
sir.
this pressure, indirectly the pressure I'm applying from outsource, correct? Externally I'm doing that. Therefore, here pressure is external pressure, right?
Yes, sir.
The external pressure multiplied by this A into dx, nothing but volume.
Yes, sir.
How much volume? Isn't it dV? Because I'm
Yes, sir.
considering
Because
only dx.
yes, sir.
Therefore, I'm taking only this volume in which the work is done, correct?
Yes, sir.
Therefore, work done dW is given by P external into dV. This is very important. P external into dV. Next, suppose if I'm doing the same throughout, maybe steps wise. Suppose if I'm compressing from this point to, see, this is the point, from this point to maybe almost at the end, at the bottom of the place, bottom of the
Yes.
vessel. If I'm doing sequentially, one after one step after another step, like that. For the first compression, I'll get work done dw1, correct?
Yes,
and
sir.
and after that, for the second compression, I'll get dw2, and the third compression dw3, and so on. I'll get,
So
yeah, after all,
infinite.
if I get the overall work done because of PV, how would I get it? Simply by integrating.
So integrated from
Yes,
H to
from
L.
A to B.
Sir.
Suppose if my starting point is A and ending point is B. Yes.
Yes, sir.
Therefore,
Yes,
ultimately,
sir.
upon integration of dw, nothing but simply w, I'll get, right? Because integration at d will get nullified.
Sir, we
Yeah,
can't.
W, sir. Yes,
Sir,
sir.
we can't compress it all the way up to the bottom, right?
Of course, man, there is a gap between here still. Okay.
Yes, sir.
Therefore, the overall work done is given by simply integral. The volume changes from V1 to V2,
V2.
correct?
Sir.
Yes, sir.
And P external multiplied by dV, correct?
Yes, sir.
Yes, sir.
So this is the